All right, we'll probably have time to go back to the problems we did on Tuesday if we need to and go over those. Okay, but we just need to finish this up. That way everything is, all the material is covered, and then on Tuesday we'll review as well. So be sure you bring questions from the homework or whatever. Okay, so we've looked at all the reactions in the gas phase, and so we have a relationship here between what we call Kc and Kp. Okay, there's really, it's a very simple difference here. Okay, Kc, we've been plugging in what into the equation for Kc? What numbers go here? Equilibrium concentrations, exactly. Okay, and then each raised to the power of the coefficient. Okay, so we can plug in the concentrations of our products over reactants, or if we're in the gas phase and we know the pressure of these gases, we can plug in the pressures as well. So here's where you'd have pressure of HCl, pressure oxygen. Okay, and so these might be, one's common, ATM, or bless you. So we can do both. We can put that into the same equation, and then we can also relate the two. All right, so here is an equation, and I'm going to give you this equation. I'm not going to have you memorize it. I don't think it's something that you'll remember 6 months from now if you sit there and memorize it. But we can relate Kp and Kc. Okay, so this is how we would do that. So Kp is equal to Kc, so that's what we've been using, times R. R is a constant, so I'll give you that. So R, I think I have it up here, yep, is 0.0821 liters ATM moles Kelvin. Okay. T is for temperature, and that has to be in Kelvin, so we know how to do that, add 273. Okay, and then that little superscript here is our change of N. Okay, change of N is the number of total moles of products minus reactants. Okay, so if we look here, so I'm going to have you come up, and I have the answer here, but you're going to use your calculator and make sure that you can do this. But if you look at this reaction here, how many moles do we have of ammonia? 2. Okay, and then we have how many moles of reactants? 4, right? So we have 3, 4. So 2 minus 4 is -2. So you can have negative numbers here. Okay, and so what I want you to do is you're given Kc, so I want you to find Kp. So there it is right there. So you would plug in Kc is 0.286 times R, which is 0.0821, times T, which is 500 degrees C, which in kelvins, that's going to be what? 773. Okay, and this is all to the power of what? -2. Okay, and so plug that in because I want you to use your calculator because this is, there's not a whole lot of these on the exam, but there are maybe 1 or 2. And they're missed just because people can't plug it into their calculator. Okay, I give you everything. I give you the formula, R, the temperature, but for some reason the exponents get off or you can't plug it into your calculator correctly. So, okay, the answer's already up there, so I want you just to be sure. If you need to, break it into 2 parts. Do R times T, and then do it to the power of -2, and then multiply that times the Kc. Okay, you're better off spending more time. Do what? Yep. All right, so just be sure you get the same answer. Okay. Do what now?
-2 came from the mole.
Yeah, the change of N. Yep. So it's really just being able to plug it in. So it's not, and just showing you have a relationship. So we can look at pressures or we can look at concentrations. You can think of C as just stands for concentration, and we can relate the two. So if we had one, so say we knew the pressures of all of the gases, we would be able to also find Kc, okay, because we could use this equation and relate the two. All right, so everybody getting 7.10 times 10 to the -5th? Not yet. I'll give you another minute to Be sure you get it. Did you break it down? Okay, do R, 0.0821 times T, which is 73, and write that number down. Okay, then that's going to be, whoa. Take that number that you just found and raise it to the power of -2. Don't use the 0.286 yet. Okay. Okay. Okay, now take that number and multiply it times 0.286. Okay. Yeah, it's just not in scientific notation. Yep. Okay, so we could do this for either one. Here we're given Kc, or we could be given Kp. Okay, so all we're doing is relating Kc and Kp. Kc being concentration, and Kp being pressures. Okay, any other questions? Y'all need another second? Okay. Yep, some calculators will do it for you correctly. It just depends on which one you have. Some, like mine, I can plug it all in and it'll do it.
I think I tend to
But
make mistakes when I break it down.
yeah, it's better to take more time. Okay, we're going to move on real quick. Did I put what? Yes. Yes. Yeah, I didn't realize it was an old version, but I changed it yesterday because he noticed. Yeah. Yeah, I change it up all the time, so sometimes it won't be right anyways, but if I change it the night before or the day of, but.
Wait a minute, now there's something, I print myself out before the chapter.
Yeah, it's still got most everything in there, but I make little changes. Yeah, so she was just asking. Okay, so we have talked about delta G the last time. So if we have a negative delta G, that means the reaction is what? Remember? Spontaneous. Okay. All right. And if we have a positive delta G, it means it's non-spontaneous. Okay. So delta G had nothing to do with rate, right? It just had to do with will the reaction occur on its own. Okay. Now we've been talking about Kc. So if Kc is greater than 1, what does that mean? The equilibrium favors what? The products, exactly. So it's product favored. Okay, if Kc is less than 1, it means it is what? Reactant favored, okay? All right. So all we're going to do now is we're going to take delta G again. So last unit, you all used this delta G equation, right? Okay, so we plugged in enthalpy, entropy, temperature to determine if a reaction was spontaneous or not. Okay? There's another delta G equation that's right here that you have to know. Okay, this is a very important equation. So if any of you go on in chemistry, you will see this again. I actually one of my first times I ever had to get up in front of professors at Alabama, and they like quizzed me on all this stuff, and I had to just spout out answers through, it's like a big, I don't know, just drill you session. And the first question they asked me was this, and I had to go through this problem and derive it, and it took me a while. So if you go on, which I know not all of you are going to chemistry for grad school like I did, but even in organic, we go back to this. Okay, so it's very important that you know this if you go on, but also just for our class, because this tells us the spontaneity. Okay, so is it going to be spontaneous or not? And it relates it to if it's going to be product favored or reactant favored. Okay, so the equation is, we could go through how to derive it, and I'm sure Michael would love to do that, but we're not going to spend the time to do it. So you end up with delta G, and not just means, at a constant pressure here, okay, is negative RT. Okay, R is a constant, okay. Notice how our units change, so R is different. That's why I'll give you R on the exam, because R can be 0.0821 or it can be 8.314, depending on the units, okay. Temperature is also in Kelvin, so same idea there. Okay, and then this is natural log of K. Okay, and K can be, we'll see this in a second, K can be KC, KP, or just K. And we'll look at the difference in those here in a minute. Okay, so here's the difference in the Ks. If your reaction is, they're all gases, then you would write K representing just Kp, okay? But the main thing you want to know here is you can plug anything into these. You can plug any state of matter, I guess, besides solid, because we're not going to be working with those. If you have all solutions, so your reactants and your products are all solutions, and you just call it Kc. Okay? Oftentimes it's just called K, because it doesn't really matter. You can plug in any of them to it. So you might have a solution, and then it forms a gas. It may form, a vapor or whatever, and then it's just called K. Okay, so don't let that confuse you when you are looking at this equation here. We could say delta G equals negative RT natural log of Kp, or Kc, or K. Okay, so don't let that confuse you. Do you have a question? Okay. All right. So we've already really stated this, but here's our relationship. If delta G is negative, we said it's spontaneous, right? If it's spontaneous, then K is going to be greater than 1. So it's going to be spontaneous in the forward direction and produce products. So this calculation is important for chemists, because they can plug in these numbers and try to determine if their reaction is going to work, one, and form products, and is it going to happen, and occur spontaneously. Okay, so that's the idea. Okay, this is pretty rare, where you end up having kind of equal concentrations of reactants and products, like a 50-50 mixture. Okay, and that would be that delta G is equal to 0, and then K is exactly 1. So that's just not, something that occurs a lot of the time. Okay, if delta G is greater than 0, it's non-spontaneous in the forward direction, so it's going to be spontaneous in the reverse, right? Okay, so this is going to be reactant favored. Okay, so here's a reaction. Okay, notice everything is in the gas phase, so that we can just call that Kp, right? If you want to mark out the P and just call it K, that's fine. It doesn't really matter. Okay, so we're given Kp is equal to 4.3 times 10 to the negative 13, okay, for the decomposition of nitrogen dioxide, and we want to calculate delta G. Okay, so our new equation, so delta G is negative RT natural log of K. All right, so try to do this real quick. It should be pretty simple and pretty quick to do. Okay, you're at 25 degrees C. You got to convert that. Okay, R is the 8.314. So you take negative R times the temperature, so 25 plus 273, 298. And then nope. Yep, if we went through, and doesn't really matter here what our mole to mole ratio is. When you derive this equation, like it took that into account, but everything kind of cancels out, so you don't have any moles in this equation. Okay, we use this equation further in organic to where we can actually predict what percentage are we going to get. So sometimes you end up with two products, and which is, not what you would really desire most times, especially if it's kind of just an isomer of each other. And so you can actually use this and do a little bit more calculations and figure out what percentage of each isomer you should get. So I should get 75% of the product I want, and then maybe 25% of the one I don't want. So. So we take negative R. Don't forget that negative. It's forgotten a lot in the equation. If you have a problem like this where you have to write it out and it's not a multiple choice, write the formula. So at least, you can get a point just for showing me you know what the formula is. Okay. So you take negative R times the 298. Okay, so 25 plus 273. Okay, and then I'm just making sure you can use your natural log there. Okay, key on your calculator. Okay, some of you may have to take the natural log, take this first and then multiply it. Okay, it's all multiplication. There's no addition here, so you shouldn't be adding. Okay, so that's what I did here. Took these two numbers, that came from here, and I got 7.06 times 10 to the fourth. So if we're going to need that, and be sure you see it here, it's in joules. Okay, and that's because we were in joules here. Okay, so we end up, our kelvins cancel, so we're in joules. Okay, joules per mole of reaction. Okay, and if we convert to kilojoules, okay, that's what it would look like there. Mm-hmm. That's a constant that I'll give to you on the exam. R is a constant. It's always 8.314. All right, so if delta G is positive, so we took our Kp, or K, that we could have found, in a different way or just by using our products over reactants and found it. Okay, we plugged that in and we found delta G, and it's largely positive. So what's that tell us? That it's non-spontaneous in the forward direction. Okay, and so it's going to be reactant favored. Okay. Another way that we can use this, so I'm just going to kind of walk us through this. Okay, we have a gas phase reaction, so we have Kp. So our equilibrium constant is Kp, just meaning that the values plugged in are pressure, okay, pressure values. Okay. So if we were asked to calculate Kp this time, okay, so we're looking for Kp. Okay, this goes back to our kind of Hess's law, okay, theory, where we could find delta G by looking at our appendix. Okay, so if you look in your appendix K, I believe it is, and you can do that, or you can just look at it later or whatever. But we would take 2 moles of our product minus 1 mole of our reactant. Everybody remember this? The Hess's law, delta G. Okay, these values right here, they were in your appendix. Okay, so we could use Hess's law to find delta H, to find entropy, and to find delta G. Okay, so these values, like I said, if you want to look in your book at Appendix K, that's where these come from. Okay, these are in kilojoules in your book. Okay, so we're going to have to convert from kilojoules to joules. Okay, so we take 2 times the 51 minus the 97. Okay, that's just Hess's law. If you need to look back at that from last unit, then you may need to. All right, so we get 4.78 kilojoules, and then we're going to convert to moles. Okay, so the first thing we've done here is found delta G. Okay, so if we look at our equation here, so this is what we just found. We know these. What's our temperature? It's going to be the 278 or 298 again. R is always 8.314. Okay, and so this is what we're looking for. Okay, everybody see that? Okay, so if I gave you a problem like this, and I would give you the delta G values, the first place you would start, okay, if you don't know delta G or natural log of K or K, then you have to find delta G first if I give you those values. Okay, so you do Hess's law and products minus reactants, and you find delta G. So now we have delta G, and we're going to find it in moles because, or excuse me, joules, because our R is in joules. Okay, so our joules here, we've got 4.78 times 10 to the third joules per mole reaction. Okay, so we found delta G. We always know R. Our temperature is 298. That's given to us as 25 degrees C plus 273. Okay, and we're looking for K. Okay, so what I want you to try to do is rearrange your equation. Okay, so if we're looking for natural log of, okay, we're looking for K, but when we rearrange here, okay, that's what it's going to look like. Okay, don't pay attention to this yet. I want you to try to do this yourself. Okay, so now I want you to solve. Okay, you've got to go through. Some of you may remember your algebra here, some not. Okay, so plug in your delta G, your R, your T, and solve for K. Okay, not natural log of K, solve for K. Okay, I'm actually going to take that off so you can try to do it yourself first. Okay, so what everybody get from doing this step right here? Okay, what'd you say? Okay, I'll That's what I got. Everybody get negative 1.93 after doing just this step here? Okay. So that number there, the negative 1.93, is equal to the natural log of k. Okay, but what are we looking for? Okay, or Kp in this situation. Kp just means we're in pressures, okay, or we have all gases. Okay. Well, what do you do in algebra to isolate just k? It's just the algebra. There's a key on your calculator, exactly. Okay. Yep. So if you look at your calculator, most of you, okay, it'll be this, you push second function and push your natural log key. You see that e to the x there? Okay. All right. So what you're going to do is take e to the negative 1.93, and that gives you your Kp. So you push second function, natural log, the negative 1.93. Okay. And that gives us 0.145. Okay, notice here, I'll remind you, when you find delta G, like we did on the previous slide, you want to convert from kilojoules to joules, okay? Because in the appendix, it gives you kilojoules. Okay, you want to convert to joules because what's your unit for R? It's got joules, right? So you have to be able to cancel those out. Okay. All right, questions? We're going to practice these now. So we're going to take, well, I'm going to practice them in just a second. I'll pull up. All right, the last thing of this chapter is just a reminder. We already talked about this, but the Kp or Kcs, they have a relationship for the forward and the reverse reaction, meaning that they are reciprocal of each other. So if we were to look at the reverse reaction from what we just did, we wouldn't have to go back through and solve for the Kp. Okay? All you have to do is take one, the reciprocal, and divide it by the number that you just found. And that gives you the Kp of the reverse reaction. Okay, so there won't be a lot on this, but there may be a problem on the exam that says, you know, what's the relationship between the forward and the reverse direction with respect to Kc or K? And that would be that they are reciprocals of each other. Okay, so if you find one, then all you got to do is take the reciprocal of the other to find the reverse reaction, or whichever way you find it first. Of the number of the Kp that you just found. So if you look right here, you found Kp to be 0.145, right? For a reaction. So if you look here, okay. So we're going from N2O4 to NO2. Okay. If we reverse the reaction, okay. So we just flip it there. Whoops, wait. Then if you look at the reverse of any reaction, this is just an example. So if you find K for one direction, forward or reverse, then the other K is going to be the reciprocal of whatever number you just found for K. So you just take 1 divided by that number. 0.145 was the number you found on the previous slide. Okay, we're going to come back to these. These might be for some bonus points here in a second. I'm going to pull up. We're going to do 3 problems, so this is your homework. So if you do these, then you'll have this whole worksheet done. Okay, did anybody print these out? If you don't, I'm going to pull it up here. Yep. Okay, on the exam I would give you the equations, but we just went over them, so you should have them in your notes or look back at the slides. Okay, so this first one, you are trying to find Kp. So you're given Kc, and we know there's a formula that relates Kp and Kc. So that was the first thing we talked about. Okay, and so I'll go ahead and give it to you. That way you don't have to look back. Okay, but Kp is equal to Kc times RT change of N. Sorry. Okay, so that's all you're doing for the first one. Number 2 and 3, you're going to have to use your delta G equals negative RT, natural log of K. And so both are pretty similar there. Okay, number 2, you're given delta G, but number 3, you have to find delta G. So all 3 problems just like we just covered. Okay, so work these. Give you maybe 10 minutes or so to work them, then we'll go over them. Raise your hand if you have questions. Bless you. Yeah, R is 0.0821 for these. Do with me. There. Be 0.11. Be 0.11. Just because you start with 2 significant digits at 4.6. confusing because it is. It's just a different unit. So like R over there is in liters, ATM, moles, Kelvin, because you're in pressures and liters. And then I gave you both, either one. Yeah, so I just didn't on the homework because you can look it up. Yeah, when you're using joules now, it's gonna be 8.314 because your units change. Y'all need to get your flu shot. Coughing. See how it goes down here. What'd you get? Let me see. The first one is right. I think you're. You converted to. Okay, so kilojoules, you gotta multiply times 1,000. So, yeah, no, it's not quite over far enough. Yeah, and then once you do that, you should get this, and then take the anti-natural log or whatever it's called. You should get -7. Yeah. Just watch what you did there. Okay, you gotta convert to joules. Remember your R is in joules. Did you convert to joules? Be sure you convert the delta G from kilojoules to joules in number 2. Okay, because remember your R is in joules, so whatever your R units are, those have to be in your equation. Yeah, it's liters per ATM over moles Kelvin is the units. Do you want me to see? convert. You moved it the wrong way. It's times 1,000. And take that times 1,000 and move your decimal over 3 places. So it's going to move. Okay, if you move 3 places, it's going to go 3, 0, 0. 18,000.
300. And I leave the 2478 as 247. I tried to change that one. That's why I did that.
Where'd you get 2478 from?
RT. No?
I don't know. Did you use 8.314 and 298? Times 298. And then you got to divide that into the 18,300. Who is? .20 times the -4. Now it does.
Okay.
All right, everybody get 0.11 for the first one? Yes, no, maybe? Okay. What about this one? Everybody get that? Okay, so just remember to convert your kilojoules to joules. Okay, and then the last part, you found natural log of K, and then you have to do your second function. Yes. Yeah, technically, so I even used all my numbers. So that's a good question. I leave it as is because even the slightest little change will change your number. So just leave it all the way, use everything until you get here, then round to 3 significant digits at the end. Okay, everybody got this before I scroll down? It's going to erase it. Okay. Miss Janice would be. Flashing up there. Okay, so what's the first thing you have to do for this one? Or one of the first things you could do? Okay, write down the formula. Good. Okay. You could go ahead and convert degrees C, couldn't you, to Kelvin? Okay, but what's different about this problem compared to number 2? We found K in number 2. And we're finding K here as well. Okay, so that's not a difference.
We have to find our G.
Exactly. In the second problem, I gave you delta G. And in this problem, you have to find delta G.
So you're going to put our product minus our, use our Hess's law.
Yep, times the moles, yes. 6.20 times 10 to the negative 4. Yeah, so you find delta G and then plug it into this, just like you did in number 2. All right, Hess's law first to find delta G. And then plug delta G into your equation, whatever it is here, and there rearrange. Do the same process that you did in number 2 to find K. Some of y'all need to go home and take some vitamin C or some medicine. Lots of coughing today. It's getting to be that time of year, unfortunately. so you find delta G, products minus reactants, you should get about 152 kilojoules, and you convert that to joules. And then we do the same thing as we did in number 2. We plug in our delta G over R over T in Kelvin, and we get negative 61.35, and then we just take that number to the power of our second function, natural log there. Okay, and we should get 2.27 times 10 to the negative 27 for K. Okay, that's a really small number, right? So what does it tell us about the equilibrium? Does it drive to the left or to the right? If we have a number that's smaller than 1. K is less than 1, it drives to the reactant side. Yeah.
Think of it as deficient. Is that how I should be thinking of it? The number's deficient, so it's not going to go to the other, it's going to go back.
Yeah. Yep. All right, any questions? I want to get to these bonus questions. Anybody? There's 2 R's. That's why I'll give you both of them, because they're the same, but they have different units. So when you use it in the first one, you need it in ATMs because you're in pressure. So your unit is liters, ATM, mole, Kelvin. When you use it for the number 2 and 3, it's in joules. And so it's very similar number, it's just different units. So it can be confusing. Yeah. Yeah. Just keep all your, well, not necessarily. It just probably depended on how you round it up there, so that's fine. All right. Okay, there is a little bit of an explanation that's in the PowerPoint, but it's not the complete answer, okay? So if in the next 15 minutes, we have 2 bonus questions, okay? If y'all can come up with the right answer, then everyone, I usually break into teams, we don't have time for that. So everyone in here will get bonus points, all right, for the exam. All right, I'll give you kind of a starting place on this one. So these are 2 kind of cool questions that I like to cover. So it talks about Mars is red, so most everybody knows that, and that is due to iron oxide. And I'll go ahead and tell you it's iron 3 oxide. So you should be able to write that formula out if you know how to name from Chemistry 111. Okay, so it's iron 3 oxide. Iron 3 oxide has a reddish tint to it. So that's what's formed on Mars. Okay. It says it has a very thin atmosphere. So blah, blah, blah. This used to be thicker. Okay, the thin atmosphere doesn't retain heat well. Okay. So at night on Mars, the temperatures are about 145, and in the daytime it rises to 300. Okay, meaning that it's a lot cooler at night than in the daytime on Mars. Okay. Does Mars get redder in the daytime or at night? Okay. The reason I have these questions in here because they go along with what we're doing in equilibrium. So what you need to do first is determine what, you know, we're forming iron 3 oxide, right? So that's going to be one of your products. You need to find out what if the temperature, well, we know our temperatures, we need to find out if it's exo or endothermic reaction. Okay, you're going to have an equilibrium reaction. Okay, so I'm probably giving a little too much information. Okay, but how do we form the iron 3 oxide? Okay, what's the reaction? And then look at it, and if you know if it's exo or endo, you can determine if it gets cooler or hotter, which way the reaction will shift. What makes it red is the iron 3 oxide. So the way that if it shifts towards the iron 3 oxide, Mars is has a redder tint at night than in the daytime. Okay, so you can Google whatever you want to do. You can use my computer. Okay, you need to come up with this one as well as, so you may want to break into teams anyways. And then the second one, what equilibrium have you disturbed when you hold your breath too long? Okay, and we'll talk about it in a little more detail. Okay? So 1 and 2 here. I don't hear any talking. Y'all better get going. So you got about 10 minutes, 10, 12 minutes to figure these two out. Okay? So if somebody wants the equilibrium with the breath, that one's a little bit easier probably than the first one. Okay, so you can Google it, or if somebody wants to use the computer. So you got to answer, does Mars get redder in the daytime or night? And then also, why? We have to explain it. If you're working on the Mars, you want to come up with your equation. I already told you the iron 3 oxide is formed. Find out if it's exo or endothermic. And if it's iron and oxide, oxygen, then guess what? Your reactants have to include iron and oxygen, right, to form the products. Anybody want to use this computer? You know what the question is. You can look up whatever you want. Most people have phones. If any of you are in anatomy or have had anatomy, then the second one goes along with what's going on in our bodies, in our blood. Do what? Okay, you don't have to, it doesn't matter. I can tell you it's wrong and y'all keep working on it. So, do what? Yeah. Okay. Okay. Yep. Now I want you to think about what's in your blood. Okay, so what's going to build up in your blood if you hold your breath too long? Do what? Okay, carbon dioxide and water are in equilibrium with something else in your blood. So find that out. So it's an equilibrium equation that you want to write. But you've got the reactants, so you've got water and CO2. Not really worried about the nitrogen and everything so much, because in our respiration, think about in your body, you're not really, the nitrogen's not what's we're concerned with. In our blood, like they said, you've got water and CO2. Okay, that's because through photosynthesis, that's what our plants produce, right? So that's what we take in, okay? But it's in equilibrium with something else in our blood, okay? So H2O and CO2 form a compound. But you're right. So what did you say is going to build up if you hold your breath? Yes. So you're right on track. You just got to think of what's going to happen. I've got some people on track with the equilibrium, the holding your breath too long. Anybody over here working on the Mars one? Okay, I already told you what the product was, iron 3 oxide, right? Okay. So what's your reactance if you form iron 3 oxide? Okay. You can Google whether or not it's an endo or exothermic reaction to be able to find that out. So there you go. Okay, so what's that? So write all this out that you're talking about. You told me you have water and CO2, right? In equilibrium with, looks like y'all are going to get one of the questions anyways, I think. Okay. Okay. So now I want you to explain it. So that's all you have left. Explain it with respect to, think about Le Chatelet's principle. Okay, what's wrong here? You only have one reaction arrow. There you go. Okay. Okay. Very good. Yep. We've got one. We've got one answer, so we'll say it out loud in a second. I don't see anybody on track with this one. So here's you some insight. I'm giving you lots of hints here. But I'm not giving you the full answer. It can. The carbonic acid, but they've got, yeah. All right, let's go over this one. I may give you till Tuesday. I'm not going to give you the answer. So we'll talk about the other one on Tuesday. All right, we had, went over here, all these guys over here pretty much kind of worked together, and Breck ended up figuring it out completely. Okay, we have an equilibrium reaction in our body. So it goes back to, so photosynthesis, right? So plants, what do they produce? They take in oxygen and what? What do they make that we can eat? Sugar, right? Yeah. Okay, and so what we do is we take in that oxygen and that glucose, C6H12O6, and we form water, actually 6 water and 6 oxygen. Okay, plus we get some energy. Okay, so I'm just going to give you the little, any of you taking anatomy, this is just stuff you should know anyways. Okay, so this is what our body does. We would take in the oxygen here, and so this is just kind of our respiration. Okay, and we produce, okay, or we now take in water and oxygen. Okay, so we take that in plus energy, and in our blood we have, okay, so the main thing's right here. So water, okay, listen up. if you want the bonus points here. Okay, I want everybody to at least understand it if you didn't get to it. All right, so we've got water and oxygen plus energy in equilibrium with carbonic acid. So this is what's going on in respiration in our blood. Okay, I'm sorry. I think, sorry, CO2. The oxygen's up here. Okay, so from this point to carbonic acid, now that makes sense, it bounces. Okay, so if we hold our breath, what are we building up? Yeah, the carbon dioxide. So we can think about, we sit there and hold our breath, hold our breath, hold our breath. Have you ever heard like a little kid, or even like when my grandmother got really old and a little bit crazy, she told me she was just going to hold her breath till she died. And I told her she couldn't do that. I said, go ahead, try. Because if you hold your breath, okay, yeah, you're going to pass out, and then what are you going to do? And then you're going to breathe. Yeah, so if anybody ever tells you they're going to hold their breath till they die, they can't. Okay, so yeah, I just say, okay, that's better than an alternative, you know. So if you increase the CO2, which way are you driving the equilibrium? Towards the products. Okay, what principle tells us that? Well, Chatelet's. If we increase on one side, we shift the equilibrium to the other. So if you build up, so essentially you're building up carbonic acid in your blood, and it's going to make you dizzy. And then eventually, if you hold it long enough, most kids can't last that long, even enough to pass out. But you're going to pass out and breathe, and then your process will shift back, and you'll get back to equilibrium. So you're disturbing it, but you're going to get back to it no matter what. Nobody can actually hold their breath till they die. When you what? Yeah. All right. So keep thinking about the other one. I'm not going to give you the answer. So if anybody has it on Tuesday when we're reviewing, or most of you hopefully will look it up, then I might give points, but I will give points for this one. So, but I will see you all on Tuesday. Have your homework. Have a good weekend. Y'all get well. All of you that are coughing, go home and